Hello viewers, today I'll be covering a topic, rock mechanics behind the raveling formation of cavity of as big as 91-meter high into 70-meter long into 45-meter wide sized that formed through crown of downstream surge gallery of PUNATSANGCHHU-II hydroelectric project Bhutan. The term geological surprises is very often taken a refuge of to cover up the lack of information gathered through geological investigations and to prepare the designs accordingly to safeguard certain situations which later on become unavoidable and cause failures. The presentation is a result of my pursuit of truth, which stands vindicated by the international literature I'll be quoting in the presentation, and also by the Norwegian Geotechnical Institute's findings, which are also presented in this presentation, and also these are vindicated by the results of 3D numerical analysis that was done by a premier institute, National Institute of Rockmechanics. A massive rock mass failure occurred in downstream surge gallery of PUNATSANGCHHU-II hydroelectric project on 3rd March 2016. There was no attempt made to bring out a scientific explanation by either the designers or the project authority or the consultants to what did cause the failure. 6 technicians were buried dead under the falling muck. 3 of the bodies still lay buried unrecovered. I tried to study various aspects associated with the failure, and therefore the following is the presentation of my pursuit of truth, which many authorities have shied away from acknowledging and come forth with the explanation. I'll be talking about rock mechanics behind the raveling formation of the cavity, which was as big as a field of football and as big in height as 1/3 of the height of Eiffel Tower. To give an insight what the designers failed to see and acknowledge as coming, and therefore failed to analyze and provide design for, which ultimately resulted in the raveling cavity formation of that big a size through the crown of downstream surge gallery of PUNATSANGCHHU-II project. There are many geological features that were not investigated by the consultants, and no proper analysis therefore could have been or was done to foresee any situation which could have resulted in such a big failure. I'll be talking in detail about all the aspects which lead to the failure and understand the rock mechanics behind that phenomenon. As an introduction to instability mechanisms of underground caverns, we understand that there are basically 2 kinds of instabilities that the underground structures come across. One where the gravity induced, structurally controlled, and block movement caused structural instability happens. This is shown in the left side diagram. And if the gravity induced, structurally controlled, and block movement caused structural instability is accompanied by loss of confining stresses, then it can produce raveling. We'll be covering this phenomenon in detail in this presentation. However, there is another case of instabilities which are stress-induced spalling due to adversely high rock stresses. That is given in the right side diagram. In this presentation, I'll be talking about the gravity-induced, structurally controlled, and block movement caused structural instability, which happened in the case of PUNATSANGCHHU-II hydroelectric project's downstream surge gallery. Let's understand the mechanism of massive rock mass failure in the downstream surge gallery of PUNATSANGCHHU-II hydroelectric project. PUNATSANGCHHU-II hydroelectric project is designed to produce 1020 megawatt and is situated at the tail end of the PUNATSANGCHHU-I hydroelectric project, which is also under construction. PUNATSANGCHHU-II project starts where the TRT outfall of PUNATSANGCHHU-I is located. A dam is to be built, is under construction on the PUNATSANGCHHU river, which flows this way. There are 4 intake tunnels that lead to desilting chambers, 4 desilting chambers, and to one headrace tunnel, which is around 13 kilometers long, which finally was designed to fall into the river back when the surface powerhouse was designed as a powerhouse. For some environmental reasons, consultants shifted this location of surface powerhouse to 3 kilometers, around 3 kilometers inside the hill. The right side hill of the valley is stronger in its structural features than the left side hill. Therefore, the surface powerhouse location was shifted to an underground powerhouse location 3.1 kilometer inside the tunnel, and what was earlier to be the headrace tunnel of 3.1 kilometer eventually became a tail race tunnel to bring the water back to the river to the same location. With this change, there was a necessity of introducing a downstream surge gallery because there was a 3.1 kilometer long tail race tunnel introduced. The consultants for the project are WAPCOs, and the design consultants are Central Water Commission, and the geology consultants are Geological Survey of India. The massive rock mass failure happened 3 years after the excavation of the crown. In this slide, we'll try to take note of 3 important points. First is that the massive rock mass failure had happened only after 3 years after the excavation of the crown. The crown was standing for 3 years intact. Excavation having started in somewhere around March 2013 until March 2016. The crown was fairly stable and was standing intact. When the rock mass failure happened 3 years after, in March 2016. Second point to take note of is that the rockfall took place in a very short interval of time, leading to formation of a huge cavity above the crown. Third point which should be taken note of is that the fallen rock mass comprise variable size of large fragmented rock pieces, sandy clay and dry clay fractions. The fallen big rock blocks sometimes range to a size of 9 meter into 1.5 meter into 3 meter. Having started in March 2013, excavation in the 3 caverns, one of the machine hall and the other of transformer hall and that of downstream surge gallery, they stood as on 2nd March 2016 to a stage shown in the green color. The machine hall with its height of around 52 meter was almost fully excavated. The bus ducts were fully excavated. The transformer hall was fully excavated. And the downstream surge gallery, out of its total height of 58.5 meter, the excavation had proceeded to a depth of 35 to 40 meters. I mentioned that the powerhouse downstream wall had 6 openings for the downstream in its downstream wall, 6 openings of the draft tube tunnels, 5 openings of huge bus ducts connecting tunnel and emergency exit. There were 4 pressure shafts, 6 pressure shafts entering into the upstream wall of the powerhouse cavern. So with these openings in the 2 walls, the walls of machine hall were more vulnerable to any instability. Similarly, and moreover, the machine hall was excavated to its height of 52 meter, whereas downstream surge gallery was excavated only to the height of 30 to 45 meter. So which looks more vulnerable, the machine hall was not facing any instability of the order which downstream surge gallery eventually had to meet with. Is intriguing. Then also it is intriguing that why did rock mass in the crown fail while excavation was underway in benching at 40 meter below the crown? Why did the rock mass fail suddenly and extended to make a 91 meter high cavity with very large base? Sorry for the spellings of fail here as a typographical error. So this point is also very intriguing, that why did the rock mass fail suddenly and extended to make a 91 meter high cavity with a very large base in no time, almost no time? Why did the cavity created of 91 meter into 70 meter into 45 meter size remain without progressing in size to a similar scale for years after March 2016, without being stabilized or supported by any strengthening that could have been done for years together after March 2016. We'll try to find out answers to all these points in coming slides. First, let us find whether the massive rock mass failure in downstream surge gallery cavern was inevitable. Actually, the designers were warned beforehand in 2014. The design consultants were furnished in 2014 a numerical analysis performed by the contracting agency for construction of powerhouse. That analysis did establish that upon adopting the given designs, a massive yielding of rock mass would be occurring in the intermediate rock pillar when the downstream surge gallery would be excavated to 2/3 height, that is around 38 meter, and this yielding would increase further with progress of excavation in the downstream surge gallery to its full height of 58 meter. But unfortunately, the design consultants did not pay heed to this analysis and they snubbed the analysis. But see that is it not ironical that excavated height of downstream surge gallery was indeed at its middle third, that is of the order of 30 to 40 meter on 3rd March 2016 when the massive rock fall happened in the downstream surge cavern. This slide shows the analysis performed in 2014 and given to the designers, which showed massive yielding in the zone of rock mass in the rock pillar between downstream surge gallery and the transformer hall. This zone of yielding was found when the excavation would have reached 2/3 of the height of downstream surge gallery, that is around 38 meters, and the zone of yielding was shown as increased when the height of downstream surge gallery would have been excavated to its full height of 58 meter. Eventually, a cavity of 91 meter height, 70 meter length and 45 meter base formed Raveling through downstream surge gallery's crown on 3rd March 2016. Let us understand what is a progressive raveling and when and why does it happen. There is an International Journal of Rockmechanics and Mining Sciences which has a very beautiful paper, beautifully covered topic of progressive raveling. The title of the topic is Stress, Instability and Design of Underground Excavations by the authors C.D. Marthina, P.K. Kasserb, R. Kischanos. It covers a case of open stopes. It gives the sequence of stoping. These circled numbers 1, 2, 3, 4. They show the sequence of excavation of these stopes. The stop number 3300, stop 3300 was stable until mining of the stop 3400 commenced. This wall of the stop was a hanging wall. We'll be seeing it in the next slide. So this is a stop 3300 with this wall having a feature of hanging wall, and accordingly this wall is foot wall. The massive sulfide ore zone at a depth of 300 meter along strike and 45 meter in width from foot wall to hanging wall. This is 45 meter and dipped between 65 to 85 degrees. The dipping of this wall is around 65 to 85, quite a steep hanging wall. This is stop 1, that in the sequence this stop was excavated first. So stop 3300 was excavated next, and when the stop 3400 had just started with its excavation, there was a raveling failure in the stop 3300 through its hanging wall. The International Journal establishes that the transverse stops averaged 35 meter in width, 45 meter in length, and over 180 meter in height. Experience at the mine indicated stops of these dimensions were quite stable usually. However, number 3300 stop, which had similar good quality of rock mass conditions, experienced significant hanging wall problems. The hanging wall rock mass consisted of blocky norites with one subvertical joint set and approximately 1 meter spacing, and a second set of horizontal continuous joints also at approximately 1 meter spacing. So the first point to be noted is that it experienced significant hanging wall problem. The hanging wall rock mass consisted of blocky norites, blocky rock mass with one subvertical joint which was repeated approximately 1 meter spacing, and the second set of horizontal continuous joint also approximately 1 meter spacing. These fracture sets formed potential wedges in the hanging wall and backs of stops. But however, simple wedges do not usually lead to progressive raveling. There could be singled out failures of wedges, but simple wedges do not usually lead to progressive raveling, particularly when the geological strength index, as was in this stop's case, which ranged from 65 to 85, which is pretty good index, 60 to 85, which represents a compressive strength of 25 to 100 MPa, tensile strength of 0.4 to 2.65 MPa, and elastic modulus of 27 to 80 GPa. So these are pretty good parameters of rock strength and rock condition. Therefore, the geological strength index was of 60 to 85 for this stop 3300. So with all these good conditions of rock, the potential wedges formed from these set of subvertical joint and horizontal joint in the blocky rock formation, why did a raveling failure occur? So we have taken note of the rock's blocky formation made out of subvertical joint and horizontal joint, and it had pretty good geological strength index also. The paper establishes that the raveling occurs when confining stresses are less than 0. This diagram is a vertical section through the stop number 3300 looking towards mine west, showing the contours of stress sigma 3. This stress in the rock mass in this shaded area is tensile, less than 0. And this dotted line is the cavity outline. The cavity was formed from the back, in the back wall, from this to this, in the shape of this dotted line, which exactly matches with the zone where the stresses are tensile. These stresses becoming tensile become the cause of loss of confinement in this region. The blocky rock had lost its confinement in this region because of the prevailing tensile stresses in and around them. Mining of stop 2900 and 3300 was carried out without incident, with stop 3300 remaining open and stable for approximately 1 year. The mining of stop 3400 was coincident with the raveling of the 3300 hanging wall. The figure shows that because of the stop geometry, a zone of relaxation extends several tens of meters into the hanging wall of stop number 3300 after 3400 stop was excavated. So what had happened was that, having withstanding all the stresses that were there before stop number 3400 was started to be excavated, the stop number 3300 stood for 1 year. But because of the geometry of this hanging wall of stop number 3300, with stop number 3400 getting started its excavation, the stresses in this zone became tensile. It is evident from the figure that failure or raveling occurs when the confining stresses is less than 0. Sigma 3 is ranging between -1 and 0 in this region, and the cavity was formed exactly of the shape of the zone in which the negative stresses have occurred. It is pointed out in the paper that loss of ductile behavior happens due to lack of confinement pressure. More evidence is presented that the higher the confining pressure, the greater the ductility observed, and vice versa. So if the confining pressures are lesser or even tensile, then the ductility would be lost and the rock mass would depict brittle behavior. The experiments on the effect of strain rate also show that when the strain rate is increased, it makes rock appear more brittle. So these are the underlined principles for raveling. That first, the ductility would be lost if the confining pressures do not remain higher. If they become tensile, it will become brittle. And as and when the strain rate would increase, the rock would appear to be more brittle. It also talks about two forms of instability which are readily observed around the underground openings, which we had earlier discussed. The first is structurally controlled gravity-driven process leading to wedge-type falls of ground, and the other is stress-driven failure or yielding. While the maximum stress near an excavation is sensitive to variations in stress magnitude and stress ratio, It is the variability in the rock strength rather than the stress that is responsible for frequently observed variability in depth of failure and failure mode in general. So, what does it mean? It means that while the maximum stress near an excavation profile is sensitive to variation in the stress magnitude and stress ratio, which is very well understood. However, it is the variability in the rock strength rather than the stress. If the rock mass is not uniformly or homogeneously representing its strength across various dimensions of it, that variability in rock strength rather than the stress is responsible for frequently observed variability in depth of failure and failure mode in general. So now with this background, let us find answers to why did progressive raveling occur suddenly through the downstream surge gallery crown of PUNATSANGCHHU-II hydroelectric project, and that too after 3 years of stable excavation of the crown. So from that paper that we have discussed before, we understand that there are 5 prerequisites for a progressive raveling to occur. A progressive raveling occurs extending the resulting cavity from the rock fall into several tens of meters to the rock mass when the rock mass is blocky, comprising numerous joint sets. Like in the case of mining of stope number 3300, the rock mass is blocky, comprising numerous joint sets. These fracture sets form potential wedges. This is the second prerequisite, that the fracture sets should form potential wedges. There exists a significant problematic hanging wall problem. So third prerequisite is that if there's any hanging wall phenomenon happening, and that hanging wall should have some problematic features, then along with these, the fourth prerequisite, the confining stress in the hanging wall are less than 0. So the fourth prerequisite is that the confining stress in the hanging wall should be less than 0. And the fifth prerequisite is the geometry of the inclined discontinuities present in the rock mass then guide the gravity-induced and structurally controlled fall of the blocks of the rocks in hanging wall. So these 5 prerequisites, the rock mass is blocky, fracture sets form potential wedges, there exists a significant problematic hanging wall problem, the confining stresses in the hanging wall become 0, the geometry is such of the inclined discontinuities present that the gravity induced and structurally controlled fall of blocks happen in the hanging wall. With these 5 prerequisites, there are very much chances of progressive raveling happen. Along with all this, the variability in depth of failure and mode of failure is guided by the variability in the rock strength. If the rock mass does not have uniformity in its rock strength, then the depth of failure and the mode of failure will be guided by this variability. Let us examine if these 5 conditions required for a raveling failure were present in the downstream surge gallery to cause the massive and instant rock mass failure, which resulted in formation of the huge cavity. So, the first requirement for occurrence of raveling failure is whether the rock mass in the failed reach was blocky, comprising numerous joint sets. Let's find out. The rock mass classification evaluated in excavation of central gullet in downstream surge gallery was that for RD 0 to 84 it was class 3, 84 to 121 class 4, and these are the average value of geological strength index associated with these reaches, which have been evaluated by National Institute of Rock Mechanics. And from RD 121 to 140, it comprised class 5 rock mass with the geological strength index of 32, and 140 to 228 RD, the rock mass is of class 4 with an index of 47 to 48. This is that reach in which eventually the failure had happened. So this comprises of class 5 and class 4 with geological strengths of index of 32 to 47. Besides a 3.5 meter thick major shear zone at RD 124 meter with an inclination of 45 to 60 degree with an rotation of north 30 degree east, and also a number of other 0.02 to 0.3 meter thick shear seams that existed between RD 148 to 166 meter with inclination of 10 degrees and orientation of south 60 degree west with the geological strength index of merely 15 were present in these reaches. So the actual geology was poor to very poor against what it was considered by the designers as given to them by the geology consultants of being fair to good. So instead of fair to good, what was considered by the designers, the actual geology was poor to very poor. It comprises leucogranite with micaceous quartzite, biotite gneiss and pegmatite veins and bands with low dip foliations with clay coatings between them. The class 5 loose rock mass is thinly foliated, highly fractured biotite gneiss with leucogranite and crushed pegmatite having Q values of 0.19 to 0.58, where excavation progressed by merely chipping or scaling and no blasting was also required in the reach of class 5 loose rock mass. And in the class 4 rock mass, it comprised altered rock mass with Q values of 1.5 to 2, with thin shear seams and sheared, crushed and fractured rock mass. This reach was highly jointed with clay coatings along intersecting joints. Excavation progress with 0.18 to 0.36 kg per cubic meter as a charge. Slabbing and wedge failures were predominant in this reach. So in all, the downstream search gallery encountered 14 numbers of shear zones or shear seams, which were ranging from in size from 2 cm to 3.5 meter in thickness. There were 7 numbers of major joint sets, including foliation joint, which was low dip, had a direction of 10 degree to 15 degree, southwest to northwest, and the foliation spacing was 0.02 to 0.3 meter. 0.02 to 0.3 meter. Amongst these 7 numbers of major joints, besides the very flat foliation, there were joints which were subvertical and adversely oriented for wedge actions and had continuity of 10 meters to 15 meter and are generally altered and stained and showing warping and filled with silty oblique clay material, sometimes filled with crushed materials, and have 10 millimeter to 20 millimeter openings also. So this is the geology of the problematic reach. Now there are 3 kinds of information available for joint sets present in the downstream search cavern. The first set of information is as considered by the design consultants and thereafter by the National Institute of Rock Mechanics in their analysis. It represents 4 joint sets Whereas the fifth joint set, which is there present as shown in other two caverns of that is of machine hall or powerhouse cavern and transformer hall, is conspicuously missing in its representation in downstream search gallery. So these are the four joint sets that have been considered by the designers and also in the analysis by NIRM. In contrast to this, in actual excavation mapped by the resident geologist of the construction agency, the information on encountered actually during excavation as per resident geologist, the joints are J1, J3, J5, J4, J7, J8, J2, J6. So that one which is conspicuously missing and is somehow present in the shown present in the powerhouse and transformer hall has a parallelly represented joint set J7 as observed by the resident geologist. So this joint set is also actually present in the downstream search gallery, similar to what is there in the other two caverns of powerhouse and machine hall and transformer hall. There is a J2 vertical joint set which is missing to be represented in the designers or consultants comprehension. Also J6, which is also a 50-degree dip, is missing in the presentation in the 3D model by NIRM and in the designer's comprehension of the joint sets. However, when in the initial stages geological investigations were done by the consultants for tender stage, they did have included these joint sets which are similar to J2, which is found actually in the excavation, and J6, which is also of the same similar orientation. So when these joint sets were seen to be present in initial geological investigations, they are actually present in the actual excavations also. So actually these 8 joint sets need to be taken into account, out of which J8 is a shear zone, massive shear zone, and J1 are the foliations. The shear zone and the thinly foliated, highly fractured biotite gneiss and crushed leucogranite pegmatite got exposed on the left wall near SPL at RD 124 meter to RD 140 meter. Further, the crown blocky and jointed rock mass is exposed. So a major shear zone was encountered which had 45 to 60 degree dip with a N30 orientation, which was encountered in April 2013 at the crown portion between RD 124 to RD 140 meter and was extending above the crown and below on either wall, dipping towards face, that is gable and wall. So excavation was progressing from south to north, and this was also dipping, shear zone was also dipping towards face of the excavation. This diagram shows downstream search gallery cut by the inclined structural discontinuities comprising shear zone and fracture sets formed by the shear seams and subvertical and vertical joints and horizontal foliation. This red colored plane represents the shear zone, which is sharply dipping at an angle of 50 to 65 degree and is north 30 degree east in its orientation. The excavation was started from south end of the downstream search gallery. This is search gallery. downstream surge gallery, and at an RD 124 to 140, this shear zone was met in the crown, and then it was found to be cutting throughout the depth of the walls. This shear zone also did touch the transformer hall at its gable end, and the powerhouse also just merely touched at its gable end. This diagram shows that the downstream surge gallery is oriented north 10 degree east, and this is the shear zone, 3.5 meter thick shear zone, which traverses from the crown all the way in its walls at an angle of 55 to 65 degree. And these are the various joint sets which make the rock very blocky here, highly blocky here, with their joints filled with clay and fractured rock mass. This rock mass is lying over this sheared plane and making this reach of the downstream surge gallery vulnerable or problematic hanging wall. This is a larger view, zoom in. So many of the fracture sets and the shear seam and shear zone and shear seams. This is another representation of the joint sets in the downstream surge gallery in 3D. This is the shear zone with so many of the shear seams and subvertical and horizontal, subhorizontal joint sets. So it is confirmed that the first prerequisite is met. Indeed, the rock mass in reach between RD 140 to 228 meter, which was lying on the steeply inclined shear zone, comprised class 4 altered rock mass with Q value of 1.5 to 2, which is highly jointed with clay coating and crushed and fractured rock infilled along intersecting joints, and had presence of numerous thin shear seams. So this confirms that the first prerequisite of which makes the rock mass highly jointed was present there. The second prerequirement for occurrence of raveling is whether the rock mass comprised numerous potential wedges. Let's see. There is an international literature which cautions that the large numbers of adversely oriented joint sets would result in overbreaks and loose rock falls. There is a paper, 40 years with the Q system in Norway and abroad, by Nick Barton, Øystein Gimstad. It gives an interpretation from the parameters like joint set number and joint set roughness number of NGI's rock mass quality index. The interpretation is about that in underground excavations, if the ratio of Jn by Jr, that means the ratio of joint set number and roughness number parameters, that ratio of Jn by Jr, if it is greater than or equal to 6, then overbreaks are extremely likely to occur during the excavations, despite contractors' best efforts with a careful blasting. This is very important information, that if Jn by Jr ratio is greater than or equal to 6, then despite that contractor would have taken all best precautions and made all best efforts for excavation, still there will be overbreaks, and it is extremely likely to occur. In PUNATSANGCHHU-II project, the downstream surge cavern has Jn by Jr ratio of 9 to 12 as against this threshold of 6. This ratio in PUNATSANGCHHU two downstream surge galleries of 9 to 12. So it explains tendency of rock falls resulting from excavation despite use of controlled blasting and even at locations where merely scooping was used for progressing in tunneling. So poor quality rock mass exhibited vulnerability to loose falls and face extensions. This is the background that we must keep in our mind, that the poor quality rock mass in the downstream surge gallery exhibited vulnerability to loose falls and face extension because the JN by JR ratio was more than 6 and was of the order of 9 to 12. The fragmented rock mass having subvertical and adversely oriented joint sets along with subhorizontal foliation is intruded with lenses and interbedding of altered and weak material like crushed pegmatite caused frequent loose rock falls and slabbing. In many instances, the rock face at the gable end face of the excavation, despite adequately supported by ribs, used to get extended by loose fall from crown and walls in heading portion itself. Excavation in heading was achievable in stretches merely with scrapping without resorting to drilling and blasting or by occurrence of face extension. So all these occurrences indicate the poor quality of rock mass present there in this reach in the downstream surge gallery. This diagram shows how frequently the slabbing or wedges used to fail and rock mass used to fall from the excavated and well supported reaches. This stereonet shows the potential wedges in the actual geology. So the 8 numbers of joint sets J1, J2 which is subvertical, J1 is foliation which is very much flat, J2 is subvertical, J3 quite steep, J4 quite steep, J5 also quite steep, J6 also quite steep, J7 is also quite steep, and J8 itself is a shear zone. This with the crosses, quite steep shear zone. So with presence of all these 8 joint sets, these are the potential wedges formed by intersection of J3 and J7, intersection of J2 and J3, intersection of J3 and J4, intersection of shear zone J8 and J3 joint sets. All these potential wedges, they are coming within the circle of friction angle. This dotted is a friction angle location of the stereonet, and all these potential wedges are falling within the circle of friction angle. So these are the potential wedges having potential of failure. So it confirms the second check also, that indeed the rock mass in the reach between RD 140 to 228 meter, which has flat foliations and which is highly jointed and which is lying on that steeply inclined shear zone, comprised 8 sets of potential wedges with clay coating along intersecting joints and with presence of numerous sheared, crushed and fractured thin shear seams, and they had their orientations as steep to lie within the friction angle. Therefore, the slabbing and wedge failures were predominant. So the second check is also confirmed. The third requirement for occurrence of raveling failure was whether the blocky and fractured rock mass which had failed did encounter a problematic hanging wall syndrome. Let us find out. There was a 3.5 meter thick major shear zone at RD 124 meter with an inclination of 45 to 60 degree with an orientation of N 30 degree east, which resulted in formation of the hanging wall. This shear zone was initially met when the 2 construction tunnels, that is main access tunnel to powerhouse and construction array to downstream surge gallery, were in their starting reaches when a shear zone was met here. It was apprehended. The shear zone was met in construction edits and met in 2012. That time it was apprehended by the resident geologist that this shear zone may extend and cut across the caverns also, and eventually the same shear zone was encountered, which was cutting across the full depth of downstream surge gallery, and it was meeting the transformer hall at its gable end and merely touching the powerhouse machine hall cavern. So this shear zone, we'll see that it makes existence of a hanging wall. This steeply inclined shear zone produced hanging wall syndrome in the reach of 140 to 228 meter, which comprise highly jointed and fractured rock mass. So this is a shear zone, and this is class 5, very poor rock mass. This is poor rock mass of class 4 classification. This is poor to fair. So from this reach to this reach of poor rock mass, there was a hanging wall syndrome which comprised highly jointed and fractured rock mass. So this highly jointed and fractured rock mass was lying on this shear zone and exhibited syndrome of hanging wall. This hanging wall had multiple inclined discontinuities and highly jointed and fractured, as we had seen earlier also, that this is the shear zone, simply dipping shear zone, and this hanging wall is having multiple inclined discontinuities, these joint sets. Highly jointed and fractured rock mass which is prone to slide in unconfined state, because the orientation of the joint sets is such that the formed potential wedges, they all lie within the friction angle, as we had seen in the stereo net. So they are all prone to slide if they meet further the unconfined state. So the third confirmation check also is proved true, that indeed the rock mass in the reach between RD 140 to 228 meter was lying on the steeply inclined shear zone. It formed hanging wall which has following problems: has flat foliations, is highly jointed, has multiple inclined discontinuities. It comprises 8 sets of potential wedges with clay coating along the intersecting joints, with presence of numerous sheared, crushed and fractured thin shear seams. Slabbing and wedge failures were predominant because of their orientation becoming less than friction angle. Now, the fourth requirement for the occurrence of raveling failure was listed as whether the blocky and fractured rock mass in the hanging wall which failed did encounter negative confining stresses. Let us see, did it encounter negative confining stresses? For that, we start with the in situ stresses before excavation. The principal stresses were of the range of 4.14 to 5 MPa. Maximum horizontal principal stress was 4 MPa. The vertical stresses were of the range of 4 to 5, and the principal stress was major principal stress was of the range of 4 MPa. Minimum was of the range of 2 to 3 MPa. Maximum horizontal principal stress had a direction of n17 degree, whereas the longitudinal axis of the downstream surge gallery was accordingly fixed to have an orientation over its axis in the direction of n10 degree east. So according to the direction of maximum horizontal principal stress of n17 degree east, the designers did fix the longitudinal axis of the downstream surge gallery quite parallel to that in n10 degree east. there was higher stresses and poor strength of rock mass. Variability of strength. Rock mass assemblage have joints filled with highly fractured and crushed material. So this rock mass in the problematic reach had higher stresses and poor strength of rock mass. This poor strength of rock mass presented the variability of strength. The uniaxial compressive strength of the intact rock in the reach of the order was of the order of 55 MPa, and that of 3.5 meter thick shear zone was 3 MPa. This is the uniaxial compressive strength of intact rock, not the rock mass. The uniaxial compressive strength of the intact rock was 55 MPa, and that of shear zone was 3 MPa. The uniaxial compressive strength of rock mass in comparison to the rock is in the reach is the order of only 1.08 to 2.84 MPa, and the rock mass strength of the shear zone was only 0.05 MPa. So see the comparison variability of the strength of the intact rock mass, which comprises the rock mass. The intact rock exhibits strength of 55 MPa, whereas the rock mass, which comprises of these intact rock and fractured and shear zones, shear seams and clay filled joints, that rock mass exhibits only the strength of the order of compressive strength of the order of 1.08 MPa, 55 to 1.08 MPa. This is the variability of the strength range. Also, the 3.5 meter thick shear zone is only exhibiting uniaxial compressive strength of 0.15 MPa. So there is a huge difference or variability of compressive strength in the rock mass as compared to the intact rock constituents of it. The reduction of UCS of rock mass to about 2 MPa from that of 55 MPa defines the nature of the crushed and fractured state of the infilling material in the joints, and excessive number of joints present that comprise the rock mass in the failed reach. So what brings the UCS of intact rock mass of 55 MPa to that of rock mass to around 2 MPa is owing to the reason of existence of crushed and fractured state of the infilling material in the joints, and there are excessive number of joints. So they together bring the rock mass to a strength of merely 2 MPa. The in situ maximum vertical stress in unexcavated downstream surge gallery cavern between 136 to 195 meter RDs were of the order of 5 MPa. And this 5 MPa is in itself higher than the UCS of the rock mass, which is 1 to 2.8 MPa. So initially also the entire rock mass was quite under a condition of stress of 5 MPa as compared to its rock mass strength of 1.1 to 2.8 MPa. State of stress versus stability in excavated underground openings. So let us see how the range of stresses influence the stability in the excavated underground openings. Moderate stresses around an excavated section are usually favorable for stability. If there are moderate stresses around an excavated section, they are welcome. They usually make the conditions favorable for the stability of the excavated cavern. Low stresses around the excavated section are often unfavorable for the stability. Major principal stresses in the downstream surge cavern are oriented along the direction of longitudinal axis of the downstream surge cavern. We saw that the major principal stresses had an orientation of n17 degree, and the longitudinal axis were having an direction of n10 degree, so they were fairly in the similar direction. Whereas the minimum principal stresses in the downstream surge cavern are oriented along direction of transverse axis to the downstream surge cavern. The layout of cavern was so designed that the minimum principal stresses so oriented were aimed to provide confining pressure to retain arch action in the downstream surge gallery crown. So as a favored feature, that the minimum principal stresses should be so oriented that they should be able to provide the confining stresses for the rock blocks to make a stable arch in the crown. So that confining pressure is very much a prerequisite for stability of the crown. The layout of the cavern is so designed that the minimum principal stresses should provide the confining pressure for stability of the arch. Now let us see whether this confining pressure was there or not. A 3D analysis of the PUNATSANGCHHU-II powerhouse complex was performed by the premier organization of National Institute of Rockmechanics of India, but it was performed 2 years after the rockfall at the request of the consultants, and it incorporated the joint sets as inferred by the consultants initially at the construction stage. So please bear in the mind that this analysis done by NIRM has representation of joint sets as conceived by the consultants at the initial stage of construction and are not based on the actual joint sets, which were more in number and more in severity than what it were conceived by the consultants in the initial stages of construction. There are three informations of joint sets that we had earlier discussed: inferred at the tender stage of drawings, inferred by the consultants initially at the construction stage, which is adopted by NIRM in its design. However, there was as inferred by the resident geologist of the construction agency during actual excavation of the downstream search gallery. This joint sets we saw in the stereo nets, they were actually present, whereas that inferred by 4 joint sets inferred by the consultants and designers have been adopted by NIRM in their analysis. This is the information at the tender stage, that these joint sets were conceived to be present. However, 2 joint sets were not later on considered by the designers. These 2 joint sets which were there in the tender stage were not, they didn't find place in the joint sets mentioned by the designers, and however the resident geologist of the construction agency states that there are these 8 joint sets. So the NIRM's analysis takes care of these 4 joint sets plus the shear zone and the shear seams, whereas in an actual there were 1, 2, 3 more joint sets which are left out in the representation in the analysis. J7 is not there, J2 is not there, which is vertical, J6 is not there in the analysis. So as discussed earlier, these are the joint sets which are actually present in the downstream search gallery. J1 foliation, J2 subvertical, J3, J4, J5, J6 and J7. Along with this, the shear zone, major shear zone J8. And this gives rise to all these 8 potential wedges: J5 and J4 intersection, J2 and J5, J5 and J7, J3 and J7, J2 and J3, J3 and J4, J3 and J8, J3 and J6 intersections. The 3D analysis of PUNATSANGCHHU-II powerhouse complex by NIRM, done 2 years after the rockfall, is based on conservative representation of joint sets. As we have seen, the 3D discontinuum model analysis of the powerhouse complex was carried out upon request in 2018 by the National Institute of Rock Mechanics, incorporating the various parameters like rock properties, rock mass joints, rock support and rock reinforcement, and the sectional properties as considered by the designer consultants in their designs, which was based only on the geological investigation report of the consultants. However, as per geological interpretation made by the resident geologist of contracting agency for construction of powerhouse complex, there were other additional distinct prominent joint sets present, as we have seen in the stereo net. These other joint sets represent sets comprising of one set dipping vertical in north 40° east direction, another dipping 50° north 55° east, and the other set dipping 40° southwest with 65° orientation. These don't find their place in the representation in the 3D numerical model. The representation of actual joint sets, including these additional joint sets, would have definitely made the 3D numerical analysis result in finding the scenario of excavation of DSG more critical and much more unsafe. We'll see that even with the lesser representation of joint sets, the conditions in the excavated caverns are not stable, and if the actual all the joint sets would have been represented in the analysis, the DSG would have been found to be more critical and much more unsafe. So let us explore stress conditions present even through this analysis, which is having representation of less critical joint sets. The results of 3D model by Niram discussed here further are of analysis based on the joint sets as considered by the designers and is deficient in presenting all of the actual joint sets which exist in the DSG as interpreted by the resident geologist. If all the joint sets actually present are included, the results of the analysis may be more critical than the present study. The assessment of the cavity, which is unreachable, was done through two studies. One is cross-hole tomography, and that gave a shape of the cavity like this. And the second exercise was done for assessing the cavity size was by LIDAR technology using CMS 500 camera. The shape of the cavity and the shape of the stress concentration above the crown are ironically quite similar. At different reaches 156, 166, 176, 186 and beyond, the similar conditions of stress concentrations are seen up to 100 meter of height above the crown, which were having major principal stresses of the value of 5 to 7 MPa, which was much more than the UCS of the rock mass itself of 2 MPa. So if we see that near around the crown, they were of the range of the 5 to 8 MPa at middle of the crown. This 5 to 8 MPa range, green colors, yellow colors, they are there in the near vicinity of the crown. Middle of the crown at RD 196. That means that the stress conditions starting from RD near the shear zone, which was of the order of 140 meter RD, till 196 also it was continuing to be quite stressful conditions. Longitudinal and major principal stresses are far greater than UCS of poor rock mass in the crown, extending up to several meters and up to even 100 meters of the height. The maximum principal stresses in the crown of the excavated DSG cavern are parallel to longitudinal axis of the cavern and between RD 136 to 195 are of the order of 5 to 7 MPa, which is higher than the UCS of 1 to 2.84 MPa of the rock mass. This stress condition led the crushed material and the clay filling in the highly jointed rock mass blocks to yield and disintegrate into destabilized independent rock pieces. Now the rock blocks at their joints having poor strength infilling material, when is stressed beyond its UCS, it would definitely get, the rock mass would get disintegrated under that stress because the infilling material would have yielded. The geological strength index of the rock mass indicative of the strength and deformation modulus of the order of 31 to 47 in the reach 136 to 216 meter, and that in the shear zone of the order 15 must have got further deteriorated. These are the original geological strength index considered, but with the stress conditions that we are seeing that they were of the 5 to 7 MPa, which was much more than UCS of the rock mass, definitely the geological strength index would have come down further. The geological strength index falls in this reach, which represents blocky, disturbed rock mass, to disintegrated and poorly interlocked, heavily jointed when broken rock mass. It falls in this reach. Let us explore state of minimum principal stresses. The minimum principal stresses aligned in transverse direction to the axis of a cavern should act to confine the rock mass and be effective in producing arch action in the crown. Moderate stresses are usually favorable for stability, as we had seen that in the case of downstream surge gallery also, its orientation is such that the minimum principal stress is acting in the transverse to the longitudinal axis. So in the transverse axis, the minimum principal stresses are acting, and they are supposed to be responsible for creating confining pressures for the various rock blocks constituents of an arch to make it capable of forming an arch action. So moderate stresses in the transverse direction are usually favorable for stability of the arch. Whereas in contrast to this requirement, there is complete absence of confining pressure due to the minor principal stresses aligned transversally in the crown and become tensile up to tens of meters above the crown. If we see, then this reach 0 to less than 0, these red zones, they were extending into tens of meters above the crown. These red zones were extending into tens of meters above the crown, making the stress conditions here acting in transverse direction tensile. So this arch action got lost because of the transverse stresses becoming tensile. They are either very low and negative, or are 0 above the ground and around also. This also shows that over the reach from 146, 156, 166, 176, all across, the stress conditions or the minimum principal stresses were similar, and they were all in tensile, extending into tens of meters above the crown. Also further 186, 196, 206, 216, everywhere that confining stresses were missing and they had become tensile. In the plan we see all along the length of the downstream surge gallery, the transverse direction minimum principal stresses are tensile. So the hanging wall in the reach 140 meter RD to 228 meter RD which was highly jointed and fractured rock mass, was having no confining pressure present. So in this reach there were no confining pressure available to form the arch action in the crown. Displacements at the interface of the shear zone and hanging wall were ranging from 65 mm to 100 mm. Here in the downstream surge gallery, we see the displacements are of the order of 65 to 100 mm. We'll see it in the next slide. So in the downstream wall, if we see at the SPL level, these are the displacements of the order of 10 centimeter, and in the upstream wall and the crown, the displacements are again of the order of 10 centimeter at RD 126 to 136 meter. That means immediately after the shear zone, the rock mass lying at the SPL had undergone displacements of the order of 10 centimeters. So this confirms the fourth prerequisite check also, that indeed the rock mass in the reach between RD 140 to 228 meter formed a hanging wall which had flat foliations and which is highly jointed and which is lying on the steeply inclined shear zone, comprises 8 sets of potential wedges with clay coating along intersecting joints, presence of numerous sheared, crushed and fractured thin shear seams. Further, that the confining stresses in the hanging wall above the crown and in the walls were indeed absent and in fact were tensile, which caused the rock blocks disintegrate into loosened individual rock pieces without any interlocking at their joints, while the joints contained only the already yielded clay and crushed material in them. Now the fifth requirement of the occurrence of the raveling failure was whether the discontinuities in the rock mass in the hanging wall have inclined geometry that can guide the gravity-induced and structurally controlled fall of the loosened blocks of fractured rock mass in the hanging wall. The inclined structural discontinuities present in the downstream surge gallery. The major shear zone is 45 degree to 60 degree inclined with north 30 degree orientation, which intersects the crown portion between RD 121 to 140 meters, extending above the crown and below on either walls, dipping towards face. This produces hanging wall effect in the northern side of the shear zone. The hanging wall side in downstream surge gallery comprise of blocky rock mass resulting from presence of fracture sets formed by multiple shear seams and subvertical joints and adversely oriented joints filled with clay and fractured rock mass, producing 8 sets of wedges. So, talking of the inclined discontinuities, hanging wall rock mass is jointed, fractured with inclined discontinuities forming multiple wedges with high potential of fallout that we have already discussed in the stereo net as well as on this. So there are multiple inclined discontinuities which make the highly jointed and fractured rock mass in the unconfined state prone to slide under gravity. So from the prerequisites that were required, we saw that the multiple inclined discontinuities are making the highly jointed and fractured rock mass in the unconfined state becoming prone to slide under gravity. In this reach, the confinement has been lost, discontinuities are inclined, there are potential wedges, fracture sets, which are making all these blocks prone to slide under gravity. Same thing shown here, that in this hanging wall, in this reach, the confining stresses have become zero in the jointed and fractured rock mass. They, with the presence of inclined discontinuities and fracture sets, the potential wedges are prone to slide in this reach where the confinement has become zero, or even there are tensile stresses in the transverse direction which should be responsible for creating an arch action. The geometry of the inclined discontinuities guide the gravity-induced and structurally controlled fall of the blocks of the rock in the hanging wall. So this prerequisite is also met, that the geometry of the inclined discontinuities are guiding the gravity-induced and structurally controlled fall of the blocks. So the fifth prerequisite also confirmed. Indeed, the rock mass in the reach in the hanging wall between RD 140 to 28 meter had no confining and in fact tensile stresses present in the crown and in the walls, which caused the rock blocks loosened at the clay and crushed material filled joints. The rock mass, which has flat foliations, numerous sheared, crushed and fractured thin shear seams, is intersected by multiple steep joints with adverse inclined geometry, forming 8 sets of potential wedges which are lying on the steeply inclined shear zone in a loosened state with no interlocking, are thus prone to gravity-induced and structurally controlled fall of the blocks. So absence of confining pressure in the reach of the crown in the DSG was there in the long reach. The tensile strength of rock mass in the reach 136 to 216 meters is order of 0.18 to 0.05. The tensile strength of the rock mass is of this order of 0.18 to 0.057. The minimum principal stresses between RD 136 to 216 along the transverse axis in this reach are less than 0 and are tensile and are of the order of 0.06 MPa, which is greater than the tensile strength of 0.02 MPa. So they are greater than 0.02 to 0.057. The tensile stresses being 0.06 MPa are greater than the tensile strength of the rock mass, which is causing widespread tensile failure in the rock mass in the crown and walls in the downstream surge gallery. The unconfined and loosely packed blocks of rock mass got destabilized and toppled by longitudinal principal stresses which exceeded the UCS of rock mass. These loosened rock mass failed to provide arch action in the crown of the downstream surge gallery. The loose rock blocks fell down under the gravitational force. The geometry of the discontinuities extended the zone of relaxation raveling to around 90 meters above the crown. So the rock blocks are so precariously held that a fresh rock fall had happened as soon as the debris from the earlier rock fall was tried to be removed. There were 6 bodies entrapped here. So 3 bodies were tried to be removed by clearing little bit of debris from here, but as soon as that debris was removed from here, a fresh rock fall had triggered, and within the days of the earlier fall. The fallen rock mass comprises variable size of fragmented rock pieces, sandy clay and dry clay fractions with rock blocks maximum size 9 meter into 1.5 into 3 meter. The rock fall involved loose falls under the gravitational forces of even larger rock blocks, which were loosely held together due to absence of confining pressure in transfer direction, while the material infilling their joints, comprising clay and sheared content, stood yielded from the excessive major principal stresses. The very often present yielded intrusive pegmatite veins bands also weakened the rock mass. Hook and Brown states in their book that heavily jointed rock mass behaves like an assemblage of interlocked angular particles with no significant strength under unconfined conditions. So these heavily jointed blocks in yielded rock mass suffered brittle failure and resulted in raveling of rock blocks one after the other because they were unconfined. Regular and planar joints of surfaces of blocks are seen from the fallen rock blocks. So, what is the explanation of rock mass failure in the downstream surge gallery given by Norwegian Geotechnical Institute? Let us also go through that. Findings of Norwegian Geotechnical Institute says, NGI reported after study of the DSG failure site that it is believed that the steel ribs do not and will not provide any acceptable rock support. All the ribs failed at joints and the steel ribs do not show any sign of bearing the load from the rock mass. The Norwegian Geotechnical Institute has mentioned in its findings the ribs do not show any sign of deformation and the rock pillars are more loaded. So these are the two, 2 points which are mentioned in the Norwegian Geotechnical Institute. So, what is the explanation of rock mass failure in the downstream surge gallery given by Norwegian Geotechnical Institute? Let us also go through that. Findings of Norwegian Geotechnical Institute says NGI reported after study of the DSG failure site that it is believed that the steel ribs do not and will not provide any acceptable rock support. All the ribs failed at joints and the steel ribs do not show any sign of bearing the load from the rock mass. The Norwegian Geotechnical Institute has mentioned in its findings the ribs do not show any sign of deformation and the rock pillars are more loaded. So these are the two observations that NGI has made is that it is believed that the steel ribs do not and will not provide any acceptable rock support, and that the Norwegian Geotechnical Institute has mentioned that the ribs do not show any sign of deformation because they had not taken any excessive load and they will not provide excessive support. Therefore, the ribs do not show any sign of deformation, whereas the rock pillars are seen to be loaded more. This is what NGI finds. Now, the observation we can see is that the ribs failed at the joints and the steel ribs do not show any sign of bearing the load from the rock mass. Implies that the ribs have not failed as a structural element. The ribs had fallen down along with the debris, but since they were not, since the ribs did not show any sign of bearing the load, they are not disfigured, which implies that the ribs have not failed as a structural element. The following observations of NGI corroborates that ribs had fallen due to withdrawal of their bearing support. The proof that the massive rockfall happened suddenly and in short duration lies in this, that the steel ribs which are lying fallen down are found untwisted and have their arch shape intact. These bear no sign of taking load. The bolts at the joints of the rig segments are intact. The various rib segments are found separated at connecting joints with the joint plates welds broken. These all indicate happening of an impact loading. We'll see in the next picture that these steel ribs are untwisted. This is a steel rib. They have their arch shape perfectly maintained. No twisting. No sign of bearing load, excessive load. Their bolts are also intact. It is that at their connecting plate joints, the various segments have been torn apart from the connecting plates. This shows a sudden brittle failure. Ribs do not show sign of buckling as an elastic failure from excessive loading, but are sheared at joint plate, indicating sudden brittle failure of the weld. So the weld between the rib and the connecting plate had failed because of the sudden brittle failure, and there was no sign of yielding under any load which would have shown any twisting or yielding of the ribs. NGI's observation of failure mechanism is that rock mass in the footwall of the shear zone first started to move down because of the insufficient support and stress relaxation. Later on, as the key block in the footwall moved, the rock blocks at the hanging wall moved downstream flowingly. This is what NGI concludes. NGI's observation too corroborates structural failure of the rock mass. NGI has reported that the shape of the cavity is controlled by the discontinuities. It is clear that the major mechanism of the rockfall was structurally controlled blockfall. This is NGI's finding that the major mechanism of the rockfall was structurally controlled blockfall. The orientation of the maximum horizontal stress is parallel with the axis of downstream surge gallery, which does not help to prevent the rockfall through confining on the rock blocks at the roof. So NGI also concludes that because of the absence of confining stresses, the rockfall in the roof had happened. This is the fault plane and this is the hanging wall side, and they say in the footwall there was movement and this bearing was lost, and then thereafter the stones in the rock and the hanging wall also started falling down. The rock mass in the footwall of the shear zone first started to move down because of the insufficient support and stress relaxation. This portion of the wall which is lying on the shear zone had its movement, and the rock mass in the footwall of the shear zone started move down. This portion started moving down. Later on, as a key block in the footwall moved, the rock blocks at the hanging wall, now the rock blocks in the hanging wall moved downward flowingly. Then all this started moving down flowingly. Let us explore why the massive rockfall was instantaneous. A known fact is that elastic failures have sustained process. Any elastic failure would have a sustained process, and a brittle failure will be sudden. These are the known facts. Lack of confinement pressure led to increased yielding and loss of ductile behavior, and results in vicious circle of raveling failure. Let's see. This reference stress and stability and design underground excavation, which we had earlier referred to in the paper. It's mentioned that the higher the confining pressure, the greater the ductility observed. Increasing strain rate makes rock appear brittle. Now, the absence of confining pressure in the tens of meters in the crown resulted in the fallout of rock blocks in a succession in one after the other. With increased cavity size, the effective zone of principal tensile stresses of rock mass increased. With the progressive raveling, the resulting increase in strain rate made the rock mass more brittle. So this vicious circle had fallen in. There was absence of confining pressure in about a reach of tens of meters in the crown, which is resulting in the fallout of rock blocks in succession. This increases the strain rate and it makes rock appear more brittle. The progressive raveling falls in, and the increase in the cavity size in the cavity zone, that zone of effective increase of principal tensile stresses also increases with this process of raveling, and all together this vicious circle keeps on making the progressive cycle of raveling brittle failure of rock mass happened with increased suddenness and instantaneously. NGI finding also ratified that crown fall followed failure of support in footwall. The rock we have discussed, the rock mass in the footwall of the shear zone first started to move down because of the insufficient support and stress relaxation. Distress in the wall supporting the crown, that is in the reach of transverse shear zone in DSG, that is 135 meter to 195 meter, increased as excavation in the benching progressed. Now, as the excavation was in the benching was progressing, then this particular reach of RD 135 meter to RD 195 meter in the distress wall, which was supporting the crown, was seeing movement in the footwall. The NGI findings ratify that the massive rock mass failure happened after 3 years of the crown standing stable, only when the increased deformations in the walls in DSG, which occurred due to increase in the benching depth to 40 meter in the reach of the transverse of the shear zone, in the traverse of the shear zone, resulted in the settlement of rock mass in the walls, thus resulting in failure of the bearing support to the crown. So NGI findings ratify this observation that after 3 years, when the benching was progressing in the reach, which is the traverse of the shear zone in the walls, and benching had progressed to around 40 meter in its depth, then there were settlements of the rock mass in the walls happening, which resulted in failure of support in the bearing for the crown. NGI finding also ratifies suddenness of the failure. NGI has reported that due to insufficient support and stress relaxation of the rock mass in the footwall started moving down, which was followed by rock blocks in the hanging wall moved down flowingly. So this is instantaneously happening, the rock mass is flowing. With progress in benching, the yielding of walls along the traverse of the shear zone increased extensively. The increased settlement in the wall supports of the crown thus led to failure of end support bearings of the crown and the ribs. The arch ribs in the crown eventually became unstable and the ribs fell down, broken apart at their connecting joints of its various segments without even having been subjected to any excessive load. The fallen ribs are untwisted and bear no signs of taking excessive load. The crown of the cavern itself, now bereft of the wall support at its SPL, fell down with raveling of the unconfined rock blocks moving down flowingly. It ratifies the theory that the ribs have fallen not because of the excessive load, but due to sudden impact resulted from failure of the walls in the providing any bearing support at the SPL due to the excessive yielding and settlement in the walls. Structurally controlled raveling failure of the rock blocks in the yielded rock mass followed immediately. Once the wall failed providing bearing to the crown, then the structurally controlled raveling failure of the rock blocks in the crown in the yielded rock mass followed immediately. Now these things are also observed in the instrumentation observations. Instrumentation observation explain why did the massive rockfall down in the downstream surge gallery happen after 3 years of the crown standing stable. If we see, then as the benching was progressing and it reached below SPL and further below to 584 meter, there were increase with the progressing benching in the surface movements noticed as the SPL instruments. These values were increasing 22, 34, 12 kind of. Distress in the wall seen in the extensometers were also increasing with the increase in depth of the benching. There are observations at 620 meter at 135, so near SPL levels. So all along in the upstream wall and downstream wall, we see that there is a progress in the values of the settlement. 27 in X direction, 50 mm, 28, 53, 28, 96 finally on the October 15 in the settlement had become 96 mm. So as benching was progressing, the movement and settlement in the walls in the reach where the traverse of shear zone had cut the walls was increasing. The distress also in the extensometers was also seen to be increasing. Arch action was intact in the crown in the downstream until 2nd of March of 2016. Excavation of benching in the shear zone reach from elevation 615 to 608 near RD 135 had been through June to November 2014. Sudden sinking and drifting bodily of the crown at RDs along traverse intercepted by shear zone at haunch portion in the walls was noticed to have occurred in the November 2014. Trend of increase in load, though not very significant in the load cells installed in the crown, happened in May 2015 after benching in the walls had progressed up to elevation 596. The distress in the rock above crown had not developed any significant distress till sudden fall of the crown on March 3, 2016. Crown arch was intact as a rock mass of at least 25 meter thickness, that is MPBX of 25 meter length, did not show significant distress. So these means that in a reach of the which was equal to the length of MPBX, which were not showing much of distress until 3rd March in the crown, indicated that the crown was intact as an arch with its rock mass until March 2nd. The load cell installed in the crown had developed excessive load on 2nd March suddenly. So this was the shear zone, shear plane, and this northern side of the downstream surge gallery was drifting along, sinking and moving in this direction day by day as benching was progressing in this reach of traverse of shear zone. One set of the rock anchors which was landing into the shear zone were ineffective, and this whole portion was bodily drifting, and the arch action till 2nd March was okay because this was having bodily drifting. Now when suddenly with this movement in the footwall, the bearing given by the wall to the crown failed, then this arch action also failed to exist. This shows distress in the walls at 609 meter displacements were seen at this level, 609 meter, when the benching was progressing. So all along we see the displacements were increasing in the walls at 609 meter level instrument, with increase in the depth of excavation. But there was no provision of wall beam and cable anchors provided to strengthen the walls of DSG, downstream surge gallery, which were designed only 40 meter thickness, despite that these pillars were intersected critically by a mega shear zone. Now, the intermediate pillar between the transformer hall and the downstream surge gallery was not provided with any cable anchors to strengthen the wall, and the rock pillar itself was 40 meter thick only. The 3D numerical analysis done, which is by the NIRM in 2018, shows that up to a depth of 15 meter into this rock pillar had been yielded along the traverse of this shear zone between RD 145 meter to RD 195 meter. So between RD 145 to 195 meter, this 15 meter thickness of walls in this pillar between the transformer hall and the downstream surge gallery, they stood yielded along the traverse of this shear zone. This is the shear zone, and as it was traversing through the depth of downstream surge gallery, the rock mass in this region of 15 meter depth exhibited yielding. 3D numerical analysis corroborates that the pillars of the downstream surge gallery were inherently weak due to presence of shear zone and existing geology at the stage even thus far excavated in the downstream surge cavern. So with 30 to 40 meter of depth excavated as compared to the total depth of 58 meter required of the downstream surge gallery, still the yielding was rampant in the walls of the downstream surge gallery in the reach where this shear zone was cutting the walls. So this is seen at RD 146, 156. So entire reach of the traverse of the shear zone, the strength ratio was 0 to a depth of around 15 to 10 meter inside in the pillar. But the conclusion thus becomes the cavity of 91 meter into 70 meter into 45 meter formed in quick succession. Increase of distress and yielding happened gradually for 3 years, with the progress in increase in depth of benching in both walls in downstream surge gallery in their reach, which was traversed by shear zone and fractured mass. Lack of confinement had resulted from presence of the steeply inclined massive shear zone in blocks of the rock mass in the crown, having discontinuities with the open and clay-filled joints in downstream surge gallery in the hanging wall side. Widespread yielding and increased settlement and displacement in the footwall at SPL finally resulted in failure of the wall support to the crown in bearing. As a result, the zone of relaxation and loss of confinement increased rapidly in the crown. Increased rate of loss of confinement pressure resulted in lowering the ductility of the rock mass in the crown. Raveling occurred through a zone where confining stresses were less than 0 and maximum principal stresses were far greater than the UCS of the rock mass. Crown imploded suddenly after along structural discontinuities due to brittleness resulting from increase in rate of yielding associated to the lack of confining pressure on the blocks of the rock mass. The shape of the cavity above the crown was controlled by the discontinuities in a zone having lack of confining stresses and variability of rock mass strength. So this is in nutshell is the conclusion of the phenomenon of formation of a raveling failure of cavity. With all requirements met, therefore, there was no stopping for raveling rockfall in the downstream cavern roof. The minimum principal stresses aligned transverse to the excavation section of the crown were tensile. Loss of confinement in the blocks comprising the rock mass in the crown and walls had happened. Loss of arch action and loss of bearing in the walls had happened. Fracture sets made by the shear seams, subvertical and other joint forms inclined structural discontinuities in the hanging wall, which resulted in gravity-induced fall of rock blocks. Geometry of the discontinuities in the hanging wall helped raveling of the rock blocks to several tens of meters above the ground. Variability in strength of rock mass made it behave brittle, resulting in the sudden and instant failure of rock mass. So there was no stopping to the raveling. Now there are some few points of caution to the designers, that they should beware of adverse geometry of any hanging wall present. Adversely poised fracture sets made by subvertical and other joint sets of the rock mass. These they should be aware of. Variability in the strength of rock mass, loss of confinement making rock blocks loosely held and rock mass brittle, resulting sudden raveling of loosely held rock blocks, resulting the rock blocks fall under gravity one after the other. So these things they should anticipate and be aware of in their further works. Points of caution design continues. In a reference book, Underground Excavation in the Rock by Hook and Brown, it mentions at page 10, in rock masses with strongly developed inclined structural features, excavation stability may be dominated by gravity falls and sliding along inclined discontinuities. So this is important, that in the rock masses with strongly developed inclined structural features, excavation stability may be dominated by gravity falls and sliding along inclined discontinuities. Large caverns should only be excavated in rock with adjusted total classification rating of 50 or better. This is also mentioned at page 299. Total classification rating of 50 or better should only be attempted for large caverns. The RMR rating of DSG stands evaluated of the order of 40 only. It does not encourage excavation of deep caverns, and same was cautioned against by GSI also in their investigation report too. Hook and Brown gives a flow chart which says that in hard rock masses with strongly developed inclined structural features, excavation stability may be dominated by gravity falls and sliding along the discontinuities. Rock classification system is inadequate. Rock classification system in such cases becomes inadequate. Then it says that in such cases, check for instability due to adverse geology. A check should be made for stability or instability due to adverse geology. Then it should be checked that can stability be improved by relocation and or reorientation of the excavation. So this is a major check, that under such circumstances of where the rock classification system becomes inadequate because of the dominated gravity falls and sliding along inclined discontinuities, it should be evaluated earlier that can stability be improved by relocation or reorientation of excavations. Can adequate support be provided to ensure long-term stability? It further says that if this cannot be done, then if the reorientation or relocation was not possible, then can, under these circumstances, adequate support be provided to ensure long-term stability? This should be checked next then. If no, if neither the reorientation can be resorted to and neither the adequate support can be provided, then in that case, if no, then reject that site. This is what Hook and Brown suggests, that then reject this site. If there were potential instability dominated by gravity falls and sliding along inclined discontinuities was foreseen, then in that case, if these checks establish that stability cannot be improved by relocation or reorientation and neither the adequate support would be provided, then in that case, it is only option left is to reject the site. Now, what would have been an approach to correct design in this case was to provide wall beams and cable anchors. That was not provided in the case. So, had these wall beams and cable anchors provided, there were fairly some chances that the failure would have not happened. But if these were also to be seen by designers not adequate at that stage, then they should have rejected the site, is what is advocated by Hook and Brown. Internal literature cautions imminent gravity falls and sliding along inclined features. In long-term stability, If long-term stability cannot be ensured by providing adequate supports, recommendation said be rejected. Thank you for supporting my pursuit of truth. I believe that my presentation would have given an insight into the rock mechanics behind this Raveling failure in downstream surge gallery of PUNATSANGCHHU-II and bring out the truth that what could have been done to prevent it and what should be learned from it, that in similar circumstances checks and balances should be done adequately at appropriate time, and if the appropriate designs cannot be provided, then the site should be rejected. Thank you for supporting me.